Hello, welcome to my talk, which is about 3 Perl modules, as you can see in the title, which are AnyEvent, Coro, and AIO. And now it starts. I was told in Japan you should first introduce yourself so that people have some reference who they are listening to. So my name is Marc Lehmann, my CPAN ID is M. Lehmann, and usually if you see me on the internet my nickname is Schmorp. I've written actually a lot of Perl modules, but the most well-known ones are JSON-XS, Common Sense, and DB maybe. No, actually it's not true. AnyEvent is far more popular. I was involved with some other software projects you might or might not have used or seen, such as RxBT Unicode and libev, AIO. I'm doing political steering stuff for GCC. In this talk I want to tell you how and why these 3 modules actually came into existence, because these modules of course were written because I personally had a need to fill with these, and the history of these is actually quite old. It started in 1998 around, I don't actually remember, and I had a problem. I had lots of fan-subbed anime, which is animation which are subtitled by volunteers, and if you have a lot of stuff, a lot of data, what do you want to do with it? You want to publish it. So I had to make them downloadable. So the first try at making them public was with Apache, because the Institute had an Apache server, of course, and this was destined to fail, simply because within a few days the server was becoming so popular that Apache couldn't cope with the load, mostly because there were thousands of people trying to download something at the same time, and Apache of course cannot really handle so many concurrent connections. The next thing I tried was Boa, because so many people at the time told me, use it, it's so cool, and it might have been cool if it wouldn't have crashed all the time, so that didn't work either. The last web server I tried was THTTPD, which didn't completely fail because it actually didn't crash, but it tried to memory map every single file that somebody would download, and anime files are usually quite big, like at that time 100 megabyte or more. So when 20 people were downloading something, THTTPD simply replied with a 500 error. I actually patched THTTPD to work, which wasn't so funny, but there were some other problems that forced me to basically develop my own web server. And at the time at least it had some very advanced queuing and rate limiting. Basically every time somebody wanted to download a file, it would put that connection into a queue, and people could actually look up where in the queue they are, and it was not uncommon for them to see, okay, my download will start in like 2 or 3 days, because it was such a busy server, and if you let everybody download at the same time, nobody would get more than a few bytes per second or something. Another thing which required my own web server was that also around that time a new type of program came up which is called Download Accelerator. It's basically these programs open often hundreds of connections to the same file at the same time, and this was rather unfair towards other people, so I wanted to implement some automatic means of stopping these. So when you have a problem and you want to implement something fast, you of course use Perl, quite obviously. What I started with was the event module for multiplexing all the I/O, and the reason is that to do the queuing and the blocking of people when they open too many connections, you need to communicate between all your HTTP processes, and if you only have one process that manages all connections, it's of course especially simple to share information, so it had to be event-based. The next thing that I used, which didn't exist, which I wrote for this web server, was Coro, which is a user space thread implementation for Perl. And the reason why I wanted that was pure convenience, as I will show shortly. The third module that I needed was Linux AIO, which allowed me to do disk I/O asynchronously. That means my web server could serve sockets while the disk was rather slow seeking. And this module later became AIO, which is no longer Linux specific. And the last thing that actually came into this web server 2 years ago only was AnyEvent and the EV module. So these three modules that I wrote, Coro, AIO, and AnyEvent, actually 4 modules EV, all came out of this web server project. And one lesson I learned is that, at least when serving anime files, it's all about latency and scalability. Or in other words, what use is it when you have a web server which is really the top of the benchmark list, but in real world sometimes it freezes for 10 seconds because the disk has some hiccup, and if this happens a lot, your nice upload bandwidth isn't being used. And the other lesson I learned, of course, is that you can actually write high-performance code with a rather slow or relatively slow language, namely Perl, because often you have lots of CPU at your disposal, because your real bottleneck is actually the network or the multiplexing between the sockets or the disk. And one such bottleneck that I found is read ahead in the Linux kernel. Basically what happened is when I had a certain number of connections, my bandwidth halved. And the reason for that was that each time the web server read something from the disk, Linux read a bit more, actually just twice as much. And then the web server went to the next file, and after about 400 files, it forgot about the original data it read, the cached data. That means that the disk was reading like 8 megabytes per second, but the web server could only write to the network about 4 megabytes per second. And at that time, Alan Cox wrote a patch so you could disable read ahead just for that reason. Another lesson I learned is that you can't control everything, because at one day I found that the university where the server was standing was basically unreachable for a few minutes, every 10 minutes roughly. I didn't realize that it was my fault, because what happened is that the Cisco router at the entrance of the university thought after a certain number of active TCP connections that's too much and rebooted. And then it took about 10 minutes until it again found enough active connections to reboot. And the university wasn't so happy about that, and I had to move my server elsewhere. Another lesson I learned is that Linux is actually quite dependable, or actually was quite dependable, at least at the time. In the last 5 years, I found that there have been an enormous number of bugs in Linux, which makes writing servers like this very hard, because Linux rather often goes into a mode where it just doesn't do any I/O for a few seconds. It just freezes. Most of these bugs, fortunately, have been fixed relatively recently, like a few months ago. But that was rather frustrating. So, on to Coro. Why did I write Coro? As I already said, it's because of convenience. And the main convenient feature was inversion of control, which in this case was pure win. So what is inversion of control? It's one of those terms which you often use, but which are relatively hard to define. But it's actually quite simple. Basically, in a normal callback-based program, you ask the event library, call my callback when some event happens. So basically here's an example of call me when done with some arguments, and the sub indicates a closure, which is the callback, which is to be called. In the callback, maybe I get some results, and then I can do it again with another function. And inversion of control basically just means instead of them calling me, I call them and wait until they return. So I just call me when done, which is no longer accepting a callback, but instead just blocks until it has the results and returns them. For this to work while other things are going on in your program, you need some kind of threads, because when your program is inside the call me when done function, of course you can't do anything else in that thread. It's blocked. And the main advantage is that this leads to often, not always, but often to a much more natural program flow, because if you have nested closures like this, or you can also use a state machine to do the same thing, it can quickly become very messy, especially if you want to implement loops and other stuff, like just any kind of control structure, really. So nowadays, back then, inversion of control was a bit manual work, but nowadays Coro actually makes it very easy, because if you have a callback function, for example, TCP connect from the AnyEvent socket module accepts a host name, a port, and a callback to be called as soon as the connection has been established. And if I want to do this in a blocking fashion, because I don't want to use callbacks, I can simply pass Coro rouse CB as the callback, and this creates a new callback object for TCP connect, which then returns. And then to wait for the actual results, I can use Coro rouse wait, which then returns whatever TCP connect passes to the callback. And this pattern works basically with anything that expects a callback. So I can always convert something that callback style, event style function into a normal blocking style function. And the reverse is of course also true. You can of course make anything that is using threads and is actually blocking into something that uses a callback. For example, here I have some callback, and then I create a new thread with async, and then do something blocking, which in this case is the Coro AnyEvent sleep function, because this function blocks only the current thread and not the whole process, as the built-in sleep function would do. And when it's finished, I can just call the callback. And since async only creates a new thread and doesn't actually wait until it's finished, this is the same thing as calling a function with a callback, because this code executes more or less instantly, and at some later point it calls my callback. Another very useful thing with threads is thread pools. Basically everything in the real world is somehow limited. For example, if you have a web crawler that downloads a lot of HTTP URLs, then you might be tempted to write it in a way that it downloads many such URLs at the same time. And if you're not careful and limit the number of URLs you access at the same time, or the number of sockets, then you will of course run out of file descriptors, because file descriptors are usually limited to 1024 or whatever is set. But in any case, there is a limit, and if you just blindly parallelize your program, then you will easily run into such problems. Another limited resource is of course memory and CPU. So a thread pool with Coro is relatively simple. The first, this line here creates a Coro channel, which I store in queue because it's almost the same as a queue. You can also imagine it as a kind of Unix pipe. You can put something into it on one side and get something out of it on the other side. And this 10 here actually is just the capacity of the queue, which means I can put 10 things into it without anybody reading something out of it. And when I want to put the 11th thing into it, the process would, the thread would actually block and wait until somebody removes an element. And to create the actual thread pool, I simply create as many threads as I want in a loop with async. Usually I do this statement, and it will become clear Why I do that in the next slide. Basically, this sets the name of the thread, and then I just have a while loop which gets something out of the queue. In this case, it expects a callback and then calls it, and that's my thread pool. And this thread pool, since I create 5 threads, basically does 5 things at the same time or concurrently, and not more. This is basically the limit. And the usage is very simple. You just put some callback into the queue which you want to be executed, or you can put undef into it, which, since undef in the while loop becomes the exit condition, will exit one of the threads, so you can easily adjust the number of threads at runtime as well. Or you can shut down the queue, which in this case will quit all other threads because they will continuously read undef. So why did I set the description? Because another very convenient thing at the time in Coro was the Dbag Shell, which you could simply add to any program of yours with this line or something similar. And this basically creates, today people call it a REPL, basically a little command prompt which executes whatever you type. And this is an example session from an actual program, in this case a game server. And the PS command lists all threads. And as you can see in the description column here, this is simply the string that was set earlier with a local. And the most important thing is, however, the where column. Because in an event-based program, when your program hangs at some point, like you have an HTTP download, but you never get called back, your callback is never executed, so something went wrong. Then it's often very hard to know where actually is the problem, because event-based programs don't have an intrinsic position in your program. They don't know where they actually are. And if you have a thread that actually blocks at some point, then you do have such an intrinsic position, because it's the code line where the current thread is at the moment. For example, for the last line, the music scheduler, if for some reason this thing wouldn't work anymore, I could just go into the running game server, do a PS and see, whatever does not work, it's in player.env.ext line 77. And this was more or less the biggest advantage over pure event-based programs that Coro offered. But recently I added something like this to AnyEvent 2, which I will show also today. First, on the next 3 slides, I want to talk about threads in general, threads in scripting languages and in Perl. The first thing is that Coro has in its synopsis, I think, Coro the only real threads for Perl, and I get a lot of, actually personally I don't get anything, any feedback on this line, but I can read a lot of it on Perlmoins or other forums where people say, oh, this asshole is talking about, and it's all true, all not true, and so on. So why do I call Coro the only real threads? Because, as many of you probably know, Perl also has something called iThreads. But you have to look about, first you have to look, where do these iThreads originate? They come from Windows, as basically anything broken and evil. And the problem they had on Windows is that your CPU has a memory management unit which can efficiently do copy on write cloning of big address spaces, which is used under Unix to implement fork and other things. But Windows doesn't expose this hardware functionality to the programs, so you can't implement fork efficiently on Windows. And since fork is such a common thing to use in Perl, the Windows porters basically wrote their own Unix process emulation using Windows threads, and this is what we call iThreads. The Windows process emulation, in my experience, is not very good. For example, it can easily happen that if you fork and then call exit from your child process, that then your parent process also exits. Which makes sense because exit might actually exit the whole process and not just the current thread. And it's of course also not very stable, and some things are not actually the fault of the people who coded it. For example, if you kill such a process, then all versions of Windows before Vista or Windows 7 will actually leak the stack memory, and there's no way to recover that. In any case, what these iThreads implement are simply Unix processes, because the defining thing for a thread is not that it's running in parallel with other threads, as many people think, because most threads do not actually run in parallel with other threads. The defining thing is that they share a lot of things, specifically memory. So if Perl had threads, then you would expect that if you put something into a global variable in one thread and read this global variable in another thread, you would actually get the value that was written in, so because the global variable is actually shared. But this is not the case. When you create a new thread in Perl, what Perl does is copies, and literally copies, all the data in your current Perl program. So if you have 50 megabytes of cache somewhere in some hash, then these 50 megabytes will be completely copied. And afterwards, you can't share them anymore, at least not easily. Another problem with the so-called Perl threads is that, I mentioned it, they have to emulate the memory management unit of your CPU in software, and it should be quite obvious that if you have a hardware chip which does something, then it usually is quite a bit faster than emulating the same thing in software. And the result is that, let's skip this. The result is that the threading or the iThreads, even when not used, are incurring a high overhead. For example, if you don't use the iThreads and just do something CPU intensive with your Perl, and your Perl is compiled with iThread support on x86, then you can expect at least 20% slowdown just because this option is there, and Perl always has to consult basically its software MMU. And the overheads can easily grow quite a bit bigger. And this is obviously not scalable, because if you have a program which is running at half speed, then if you are lucky enough to be able to parallelize it, so it runs on 2 CPUs at the same time, then you actually don't get anything out of it, because your program is half the speed originally. So you would need to have a high degree of parallelity to actually recoup these overheads. The next thing, which is doesn't have anything to do with Perl, is that many people, including me until a few years ago, thought that threads were actually made for scalability to multiple CPUs or multi-core systems. And what most people forget is that threads were not designed for multiple CPU operations, because they were designed for single CPU operation. Because if you have a single CPU and you have a lot of memory and you have a lot of processes, then each time there's a context switch, the registers of the CPU need to be reprogrammed. Specifically, the memory management unit needs to be reprogrammed. And the solution that people in earlier times found for this problem is to not actually replace, not actually change these registers, which had the effect of processes sharing the memory with each other. So this is what threads were designed for. And if you wanted scalability to multiple processors or multiple cores, you actually wanted to use processes. And the deeper reason for that is that, as I said, for single CPU, the CPU registers don't need to be reprogrammed. And the reason for that is that they have the same value in all threads. But if you have threads running on multiple cores, then this advantage suddenly becomes a disadvantage, because now all the CPUs have to agree on the same register state. So for example, if you have multiple threads running on different CPUs, and one of them unmaps some memory, which can happen if you freeze a memory, then the kernel has to interrupt all the other CPUs and tell them the memory has changed somehow, and this is a very, very costly process. However, as all things in reality, it's not so as black and white as I just meant. There are cases where threads can gain you a considerable speed advantage, or simply where processes are really hard to use or awkward to use. But in general, the trend is that threads are not actually the solution you should look at if you want your program to run in parallel and well. The last problem I want to talk about is about about kernel threads, which are threads actually running in parallel with other threads at the same time. And if you look at other scripting languages, you will see that none of them actually offer this. All of them offer some kind of thing called threads, but none of them actually run in parallel. And this depends on the definition of what a scripting language is. And I don't actually know what a scripting language is, but let's say for this in this time that a scripting language is something that doesn't usually crash hard when some error occurs. So in a scripting language, you don't expect your program to crash because you write a store floating point number in an integer variable. Or you don't expect memory corruption because you misuse the pointer. These are all things that you can't really do in Python or Ruby or Perl, but you can do it in languages not typically called scripting languages like C. And the basic problem is that if you want to share your memory, then you have to log everything. And the reason for that is that in C, for example, you don't have to log everything. Because if you don't get it right, if you forget to log your mutex or anything, then you get memory corruption or a crash. And, well, nobody cares. I mean, it's C, so people expect this kind of thing. But if you want to avoid this in Perl, then you actually have to log everything, which is very slow. And the other reason why you have to log it and can't do any interesting tricks is that in C, for example, an integer variable basically can be treated atomically by most CPUs, but a Perl scalar is just too big to be treated with atomic instructions. So you always have to resort to very slow mutexes or anything like that. And yes, according to my information, nobody really has solved this problem yet because of these problems. So no scripting language or no higher level language actually supports parallel threads in a meaningful way. For example, Ruby and Python, Ruby since only for a short time, have real threads, but they're actually very slow, because what they do is they make sure by locking that only one thread is ever actually running. And they use pthreads to implement that. And if you don't really care about the advantages of pthreads, namely that they can run in parallel, they are actually quite slow compared to user space implementation. To give you an idea, with Coro, I can do about 2.5 million context switches per second on my computer, and pthreads from Linux, which supposedly is very fast, which is probably also true, can only do about 200,000. So it's 2.5 million to 200,000. Because in user space, you can just do it so much faster. And even though context switch in Perl is quite high overhead, because Perl wasn't really designed for threads, it's still so much faster. There are languages which have threads in a sense, for example Erlang, but if you look at that, you can see that Erlang actually also emulates processes, because each Erlang thread has its own address space. It's impossible to share data in Erlang without actually copying it to another Erlang process. So Perl is not alone here. The Perl 6 people, of course, always have a solution for everything, and in their case it's STM, software transacted memory. And I guess since they haven't managed to get it working well yet, they haven't realized that it will not actually work, because even STM requires a lot of overhead at another place, but I doubt it will ever work. But I would be very interested if somebody actually comes up with a solution for this problem. Okay, now to something completely different. The next module is AIO, and this module implements asynchronous I/O, which means you can read from a file or write to a file while doing other things. And originally it had a wrapper for basically every POSIX call. For example, there was a wrapper called AIO open, which would open a file in the background and then eventually call your callback with a new file handle. Or there's an AIO stat call or an AIO chmod call and so on. Basically the whole POSIX API was there, and it was working just like the POSIX function, except that you added a callback at the end, which got the results at some point. Nowadays, it wraps even very esoteric stuff. For example, POSIX 2008 has a current working directory abstraction, which you can access with AIO WD, or there's a function that reads a directory and tries to give you the optimal order to start all the files in it and things like that. You can access the readerhead syscall on Linux or syncfs, sync file range, mmap, fedwise send file, whatever. So basically AIO is your toolbox for just everything your operating system supports regarding I/O, and it does that always asynchronously, so you don't have to wait for it. There's another module which comes with Coro called Coro AIO, and the only purpose of that module is to take all the requests here which take a callback and convert it into the more normal form. And it does so completely automatically, so when there's a new version of AIO, you don't actually have to download a new version of Coro to make it work with it. Here's a real-world example of how it's used. I hope it's big enough. I hope so, yeah. So the first thing, this line is actually acquiring a log. This example is taken from a Usenet news fetcher, which downloads a lot of articles. And this ensures that only one thread at the time actually writes to the disk, which wasn't necessary until very recently when XFS, which is otherwise a very nice file system, started to allocate 32 kilobytes for each file you write if more than one process or thread writes at the same time into the same directory. So I had to create a log or a semaphore that makes sure only one thread executes this code. And here's the AIO open call, and instead of using the callback in AIO, it simply blocks the current thread and returns whatever the callback would have gotten, in this case a file handle, so this creates a file. Then here is an AIO write call, which writes the data to the file handle, checks whether it works, otherwise it dies. This is a rather esoteric thing which works around the very bad performance of fsync under Linux. Basically, this is telling Linux, could you please fsync most of the file without actually stopping everything else on the computer. Then I use a rather esoteric call, which is fedwise. In this case, it's not actually asynchronous, and this call tells Linux that it can basically throw away the cache for this file because this file is not going to be accessed for a long time. Whether Linux does it or not, I don't actually know at the moment. And in the end, it fsyncs the file and closes the file handle. So this, to me, looks very natural, basically just like you write it down in normal Perl. But it runs actually in parallel with other threads and doesn't stop your process when it accesses the disk. The next module is AnyEvent, about the history. Oh my god, I have to speed up. AnyEvent came from the netfcp module, which is a completely unimportant module. It's basically a freenet client protocol implementation. And I wanted it to be event-based, and I wanted to upload it to cpan, but I didn't want to use the event module, at least not hard-coded, because that would force everybody to also use the event module. And basically, I implemented AnyEvent inside this module before it was called AnyEvent. Let's skip this. Some news about AnyEvent, some old news is the AE namespace, which has been introduced in version 4.9 of AnyEvent. I hope you all know about AnyEvent already. Basically, I realized that the event API, which uses methods to create watchers, is a mistake because it's slow, uses a lot of typing, and that isn't actually so readable after you wrote it. And because at the same time I actually was writing libev, which uses a radically different approach, a very simple one, I basically ported the EV API to AnyEvent. So the old way to create a timer was by calling the timer method in the AnyEvent module with named parameters after, meaning call my callback after so and so many seconds, interval meaning and then do it so and so many seconds again and again, and the callback it is supposed to call. And the new API is just a function call with some fixed parameters, seconds, interval, and the callback. And of course, all the other watcher creations in AnyEvent also are available in AE. And I instantly converted all my programs to this form, because if you use EV as a backend, or even the Perl module, and you do some benchmarking, you will find out that just using a method instead of a function call makes creating a watcher 5 times slower, because function methods in Perl are really so slow. However, I basically vowed to never abandon the AnyEvent namespace, so if you like the method-based approach better, that's just fine. Earlier I showed you a debugging session with the Coro shell, and a few months ago I implemented something similar for AnyEvent. I'm not exactly sure how useful it is in practice. Basically, you can create, again, a debug shell. You can bind it on a TCP board, or in this case, by setting the environment variable AE debug shell to some Unix path to Unix domain socket. You can, of course, also create it from a program by calling the respective function in AnyEvent debug, in the AnyEvent debug module, but by setting environment variable, you can access this in every AnyEvent program. And Socket is the program I use to actually connect to the Unix domain socket. Ignore the first part, go straight to the WL part, which is short for watcher list. And the watcher list command basically shows you all watchers that your program has created that are active at the moment. And as an example here, the last one. It's not as readable as with Coro, because we don't really have a program line, but what we do have is the line where the watcher was created. In this case, in a file called CF. The actual name is a bit longer, but I shortened it for this slide. In line 3749 in the begin block. There it created a signal watcher, and the callback for the signal watcher is defined in the CF file at line 77. And AnyEvent actually stores a lot of information about each watcher, which you can access with the I for info command. So if I investigate this watcher in detail, you can see again the short name, where it was created, what type it is, where the callback points to, and this is basically all the other information that is being stored. For example, the type, the arguments, the original arguments that were used to create the watcher, the time, the full path name of the file, whether tracing was enabled at the same time, the callback it uses, and the good thing is that when you normally print a code reference, you just get code and the hex number of the internal address where the CV is stored, and you can actually decode this into something human readable from pure Perl, which I only learned last year, which is the reason why this functionality was only implemented recently. So basically it decodes your code callbacks, it can tell you how often the watcher was invoked, it can give you a full backtrace of when it was created with all the arguments, and when your watcher dies, it will actually store up to 10 backtraces of the time when the error occurred, which is extremely useful in production when your watcher dies and you don't expect it to, because obviously in production you don't use stuff where you know it's broken. And this way you can actually go like days later to a customer and check the backtraces without going through some log files. Yeah, we are at the end, and one thing, have a minute, huh? I just continue with it. One other module that is new in AnyEvent is the AnyEvent log module, which is a bit like log for Perl, but much smaller, of course. And the very last thing I wanted to mention is please don't use userbin and Perl to start Perl programs. I know it's cool, I know Python does it, so we have to do it too, but Perl is basically always in userbin, and env might very likely get you the wrong Perl. At least in my system, I have a very long path variable with lots of Perls, and the first Perl is not really the Perl that might be the one that ran the makefile PL when creating a module, for example. So please just use userbin Perl and not userbin env. Thank you very much.